So the first approach to computing importances of the web pages in a big web graph is called PageRank. So what we will do now is we will come up with the first mathematical formulation of PageRank. We will first talk about it intuitively, then we'll mathematically formalize it. We will then talk also about how to actually compute the importance scores, and we will see that our initial formulation is broken, so we will then later fix it. But for now, we will just come up with the initial formulation, and this is called the flow formulation for the PageRank algorithm. So here is the idea. The idea is that we think of links on a web graph as votes, right? So the idea is that a page or a node in a graph is as important as the number of links it has. Of course, the first question is, what kind of links are we talking about? Are we talking about in-links? Are we talking about outgoing links? For example, we will look at in-links. In-links, because in-links are kind of harder to fake than outlinks. It's very easy to have a page with lots of outlinks. It's harder to have a page that lots of other pages on the web point to. So that's the first question. The second thing is that it's not enough just to consider in-links, but we also have to consider where this link is coming from. So for example, a link from a given web page, maybe from stanford.edu, is more important than a link from some other web page that only receives very few in-links. Right? So the idea is that not all in-links are equal. Kind of links coming from important pages are worth more. And here is basically the idea. The idea is that an importance of a page is in some sense depends on the importances of other pages that point to it. So we have this recursive definition where importance of your given page depends on the importances of the others, and this importance then kind of gets passed on further through the graph. So this is the first idea. And just to give you an intuition how PageRank scores of a graph look like, here in this slide I'm showing you a small graph with a set of directed edges. And here in this graph, the size of the nodes is proportional to its PageRank scores. And here I normalize the PageRank scores so that they sum to 100. And what do we see is the following. We see, for example, that node B has a very high PageRank score. The reason why it has high PageRank score is because it has lots of other pages point to it. For example, node C also has a relatively high PageRank score, even though it receives only a single incoming link. The reason why C has a high PageRank score is because this very important node B is pointing to it. And then, for example, you can see that these very small dark red links nodes have relatively small PageRank scores. For example, the PageRank score of node D is higher than the PageRank of node A because D points to A. For example, we see that the node E has kind of intermediate PageRank score and E points to B, and so on. Right? So the results we get from PageRank are kind of intuitive, and they correspond to our intuitive notion of how important is a node in a graph. So now what we will look at is how do we compute this kind of scores or importances of nodes in the graph. So the idea is the following. The idea is that we will come up with a simple recursive formulation where we think of each link as a vote, and we think of the importance of a given vote to be proportional to the importance of the source web page that is casting this vote or that is creating a link to the destination. So the way we think about this is the following. Let's think that we have a page J with an importance R sub J. And for this, let this importance be just some number. And think that the page J has n outgoing links, right? So then the way we will say is that now this importance Rj of page J basically gets split on all of its outgoing links evenly. So each link gets R sub J divided by n votes or amount of importance to spread to the target. So now this is how the importance gets from J to the pages it points to. And in a similar way, we can define the importance of J as the sum of the votes that it receives on its in-links. So if we look at the simple graph here at the bottom, the idea is that the importance R sub J of web page J is simply the importance of page I, the green page, divided by 3, because page I has 3 outlinks, plus importance of page K divided by 4, y by 4, because page K has 4 outlinks, 1, 2, 3, and 4. So this is how we compute the score of page J. And now that we have the score of page j, this score further gets propagated outside of j along the 3 outgoing links. So each of these links gets the importance of node j divided by 3. And this is basically all that is to this formulation, is every node collects the importances of the pages that point to it, has its own importance, and then kind of propagates it through their neighbors. So the idea is that basically these votes flow through the network. So that's why this is called a flow formulation or a flow model of PageRank. And just to give you an idea how this would work out, here is a very small web graph, from prehistoric times when the web only contained 3 websites, A, M, and Y. And imagine that this is the structure, right? So Y has a self link and then points to A points to M points backwards, and so on. And our initial idea, as we said before, is the vote is from an important page is worth more. So a page is more important if it's pointed to by other important pages. So as I kind of hinted on the previous slide, we will assign an importance score R to a page J, and we will call this importance score rank. So this is where the PageRank terminology comes from. So we call this importance to be rank. And now our formula that we have for computing PageRank is very simple. We simply say that the importance score of page J is simply the sum of all the other pages I that point to it, importance of that page I, divided by the out degree of the page, right? So now what we can do is basically, this means that for every node in the network, we obtain a separate equation. So for example, the importance of node Y in my network is simply the importance of Y divided by 2 plus importance of A divided by 2. So why is that? Because Y has 2 outgoing links. One link points to itself, so it's Y divided by 2. And then similarly, node A has 2 outgoing links. So we take RA and divide it by 2. For example, if you say what is the importance of node M, importance of node M is importance of node A divided by 2. Again, Y divided by 2 because node A has 2 outgoing links, and half of its importance goes to A, and half of its importance goes to Y, as we saw here, right? So now it almost seems like we are done, right? We have this set of equations that we would like to solve, right? We have 3 equations, 3 unknowns, no constraints, and we want to solve this. The problem is that this has no unique solution. The reason is that the system is under constraint. So basically, all solutions we can find an infinite set of solutions to this set of equations, and what these solutions will have in common, they will be equivalent up to the scaling factor. So we need an additional constraint. So the constraint we will add to our system is to say that our PageRank scores have to sum to 1. So Ry, Ra plus Rm has to be equal to 1. So now with this additional equation, we can basically have now 3 unknowns, 4 equations. We can go solve this. For this small graph, we can go solve this by hand, and we would come up with the solution, which are our initial PageRank scores, right? So for example, Y has score of 5/2, A has score of 5/2, and then M has score of 1/5. Right? So it seems like that we are done, right? So we could use any kind of linear system equation solving method, for example, Gaussian elimination, and be able to compute the importances of nodes in the graph. This approach would work well for very small graphs, but it won't work for a size of the web graph. So basically for a graph where we have 1 billion web pages, because it would mean that we have 1 billion of equations, a system of billion of equations that we would want to solve. So we need a different formulation.